So field forces in general. So on Sunday, one of the things that Christian was talking about, and probably something you've seen in your actual physics class, is the idea that you can categorize all forces as either contact forces or field forces, with the difference being with a contact force, it needs to actually touch the object to put a force on it. And a field force does not. It can exert a force on an object without actually touching it. So it can exert a force from a distance. So just to get us started, can somebody give me an example of a contact force? Okay, so some contact forces, if you think about things that actually need to make contact in order to exert a force. So you might say the normal force, where, a support force, if you're standing on the ground or you've got a book on a table or a block on a ramp or something like that, you've got a force that is acting perpendicularly upward from whatever the surface is. So that's a contact force, because it only happens if your feet are in contact with the ground or the book is in contact with the table. Friction is another example of a contact force. If you're that's essentially how an air hockey table works, right? So it will make the puck hover above the table so they're not in contact anymore. And so you have not exactly no friction, because you still got the air layer in there, but you've got much lower friction and the puck can kind of slide around and do all crazy stuff. So can somebody give me an example of a field force in that case? What's something that can exert a force on an object without actually touching it? Okay, so some field forces might be gravity, obviously. Another one that is maybe something that you might have experienced more directly, that idea of having two things that are not touching, but you can feel that there's a force between them. Have you ever played around with magnets, which a lot of kids, or maybe not even kids, do? If you held two magnets close to each other and felt them either pull or repel, they're repelling, it almost feels like there's something in between them, but they're not touching. So they're exerting a force on each other without touching. So that would be another example of a field force, would be magnetic force. So all forces can fall into one of these two different categories. And one other thing that's kind of a side note, but I think is sort of interesting about forces, and an excuse to put a little XKCD comic in there is always welcome. If you get down to the kind of fundamental level, looking at subatomic particles, at the very lowest level, there are really only 4 forces, period. One of which is gravity, which is kind of what we're talking about tonight. Another of them is electromagnetism. So that magnetic force that we just kind of talked about, and also the electric force as well. And then the other 2 are super descriptively called the strong force and the weak force, but both of those act on the order of things that are very, very close together, like within an atom. And so those are kind of definitely outside the scope of AP1, but you will see these 2 formulas that are right here. So you'll see the gravitational force and you'll see this electrostatic force over the course of your year. And the gravitational force we'll look at tonight. So gravitational forces or field forces in general, you can describe them as a field, which kind of hence the name. So we've got a picture here of the Earth, and these arrows are representing the gravitational field around the Earth. Earth is a really good example because that's the gravitational field that we experience kind of all the time. And as far as calculations go, that's the gravitational field that you will be dealing with most often. But it is true that everything that has mass has a gravitational field around it that would look very much like this, directed inward toward the center of mass. However, it's really only noticeable if the object has a lot of mass. So you have a gravitational field around you right now, but it's so tiny, it's pretty much negligible. But when you have something big, something supermassive like the Earth, then that's going to be something noticeable and that you'll be putting into pretty much any force problem that you end up doing over the course of your physics career. And this gravitational field it's not something that, it's not like a physical thing. It doesn't really, I don't want to say it doesn't really exist, but it kind of doesn't. It's more of like a model. It's like a construct. It's a theoretical thing. And you can define it as it's the region in which objects that also have mass will feel a gravitational force. So any object that is within the Earth's gravitational field, so like a person or the moon, obviously not to scale, both of these will feel that gravitational force because they are within the Earth's gravitational field. And it gets weaker and weaker the farther away you go from the Earth. And it kind of technically doesn't exactly go away, but it gets to a point where it's so small as to become negligible, kind of like the gravitational field around, say, a person. It also acts towards the center of the Earth. And that distance that I just talked about, how it gets weaker and weaker as you get farther away, it's not farther away from the surface of the Earth, it's farther away from the center of the Earth, or center of mass, to be specific. So that force is really kind of directed toward and acting toward the center of mass of the Earth. And when we talk about how far away you are, which will kind of play a role in the equation for this, you're measuring those distances from the center of the Earth. So the radius of the Earth will play a role if anything's standing on the surface, like that little dude in the picture. Okay, so I should have said earlier, but if you have any questions as we go through this stuff, feel free to drop a question in the chat, or you can use the Ask a Question button down there, and I'll be able to see when there are questions, and I can kind of make sure that I put them, make sure that I address them before the stream is over. And if somebody uses that Ask a Question button, you can also look at the questions that have already been asked. And if you have the same question, you can just indicate that and click on that instead of having to type the question in yourself. So if I can see like, oh, 3 people want to know about this question, then I will definitely make sure I address it. So that's just to kind of say that you can always put stuff in the chat and ask me questions at any time. Okay, so now I'm gonna ask you a question and do a quick check-in. So this one you should definitely know. What is the acceleration due to gravity? So it's negative 9.8 meters per second squared is the number we use for the acceleration of gravity. And you're better than I am. I forgot to put in the negative sign. I just put the magnitude of it and did not put in the direction. So good call, Rachel. So that was an easy one. This one is a little bit trickier, might need a little more thinking, but with what we just said, if I go back to this picture, with what we just said about the strength of that force not being constant, like it's stronger if you're closer to the Earth and weaker if you're farther away, why is it that we can treat that number like a constant? Why can we just say acceleration due to gravity is 9.8 and just use 9.8 pretty much consistently? Does anybody have any thoughts on why that might be the case? Okay, I know that's definitely a trickier question, but it's kind of analogous to the idea that from our perspective, and I know it's kind of a meme as well, but from our perspective, the Earth certainly seems like it is flat, even though we know that it is round because we are just so close to the surface and it's so big. Similarly, we're so close to the surface of the Earth that any difference in our distance from the center of the Earth when we're, at the surface, or if we're 5 meters above the surface, or I know I think it was last week, Casey did a problem where somebody dropped a phone out of a car window that was 1 meter above the Earth. Well, if the radius of the Earth is on the order of like 6 million meters, then 6 million versus 6 million and 1, not really much of a difference. And so the height difference is going to be so small relative to the actual distance from the center of the Earth that it really doesn't matter. So, to kind of think of that visually, if we picture like zooming way in, when we're zoomed out, we can see those arrows are going in all different directions towards the center, and they are noticeably closer together when you're here near the surface than they are when you're up here. But if we get closer, If we direct those arrows towards the center of the Earth, they are more or less parallel. And if we are down here at the surface versus if we were up here or something, even with this definitely not being to scale, it really doesn't matter. So we can treat that 9.8 as if it is a constant. So this kind of brings us back to, or brings us to the idea of Isaac Newton and his, I guess, insight that has to do with gravity, which I think is really, really impressive when you think about it. Like there's just no other way to say it. So what's the famous story with Isaac Newton? What's like the prop that always shows up in the story about Isaac Newton and gravity? Does anybody remember? Sitting under a tree, allegedly. We have the apple falling and poof, he figures out how gravity works. And maybe it happened something like that, maybe not. But the key insight that Isaac Newton had is just the fact that that force that caused the apple to fall and the force that causes the moon to revolve around the Earth or the planets to revolve around the sun, those are the same force. And I don't know, maybe it's just because I'm a physics nerd, but that just blows my mind. The fact that he just figured that out, because they sure don't look like the same force. If I pick up an apple and I drop it on the ground and I watch it fall straight down and I see its speed changing, and then I go out at night and I look up and I see the moon in the sky and I see how it changes from night to night, its position and its angle and stuff, it would not dawn on me at all that it is the same force that is causing both of those things to happen. So that, among other reasons, that's one reason why I think that Isaac Newton was like seriously impressive. If we are thinking about, great minds, great geniuses in the history of physics, I think he's got to kind of be up there, even if he was a little bit weird in other areas. So he came up with this law of universal gravitation, and this is in addition to the 3 laws of motion that you may have already learned about in your classes, and that we'll kind of talk about in various order over the next couple of weeks here on Fiveable. So we define gravity as a force that exists between 2 objects. So that's important. You have 2 objects that have mass. Object A pulls on object B, and object B pulls back on object A with the same amount of force. So if you are there standing on the Earth's surface, it's pretty intuitive. You can kind of tell that the Earth is pulling down on you. But what is maybe less intuitive is that you are pulling back on the Earth as well with an equal amount of force. The Earth is obviously way more massive than you are, so the effect on the Earth is not going to be nearly the same as the effect on you, but the force is the same. And the strength of that force depends on the masses of the 2 objects and the distance between them. And so this is the equation that he came up with. And he wrote it a little bit differently. He just said it was proportional to, and he didn't know what this constant was, but the magnitude of the force of gravity, so that's why we've got this absolute value symbol here, is equal to this constant big G times the masses of the 2 objects, and then divided by the distance between them squared. Okay, so we've got the masses of the 2 objects, the distance between the centers of mass of the 2 objects, and then we've got this constant G, which is equal to, if this little pop-up will go away, is equal to 6.67 times 10 to the minus 11. And then the units that you see there are just basically the units that are necessary to make that FG come out in newtons. Okay, so you have meters squared in the numerator to cancel out the meters from this distance, meter squared from this distance, and you have kilograms squared in the denominator to cancel out the kilograms from these 2 masses up here. And so if you multiply that, force will come out in newtons as it should. And that gravitational constant, just as the units for it are kind of contrived to just make things come out the way that they should, the size of it is also also contrived to kind of make things come out the way that they should. So constants like big G here are figured out experimentally. So this G was first figured out like 100 years after Newton came up with this equation by experiment. You have known masses, a known distance apart. If you're able to measure the force between them very, very carefully, then you can experimentally determine what that constant must be. So that's where these kind of numbers come from. There's nothing really super magical about 6.67 times 10 to the minus 11th. It's just that's the number that makes it work right. And so that's what the constant is. So you've also seen another equation for the force of gravity, I'm assuming. So what is the way more common one that you might have used to find the force of gravity or the weight on an object? Okay, so hopefully this looks familiar, where you've seen the force of gravity is equal to mg. And a lot of times you wouldn't even use this Fg here. You would just label it as mg in a free body diagram and just use it as mg all the time. So it's the mass of an object times the acceleration due to gravity, that 9.8 meters per second squared, will give you the force of gravity on that object. And then you could use that in your free body diagram, and you could use it in all sorts of ways depending on the context of the problem. But it can be interesting to see where that comes from. And so I figured it might be worth it to kind of go through that derivation just a little bit. So we have here our two equations for the force of gravity. We have the more familiar Fg equals mg, the small g, meaning 9.8. And then we have Fg equals big G, so the 6.67 times 10 to the minus 11, times the two masses divided by the distance between them squared. And so let's say that our two masses are person and the Earth. So we'll call the person m1. The Earth will be m2. So m2 will just literally be the mass of the Earth. And then the distance between them will be the distance between their centers of masses, which will pretty much be the radius of the Earth. Again, the radius of the Earth plus the distance from the ground to the person's center of mass, but excuse me, that's going to be so small compared to the radius of the Earth, we can pretty much just use the radius of the Earth. So since this is equal to Fg, the force of gravity, and this is also equal to Fg, the force of gravity, then we can set them equal to each other, right? If they're both equal to the same thing, then they must also be equal to each other. And one thing that we should notice here is that we have an m on this side of the equation, and we have two m's on this side of the equation, but one of them is going to cancel out with this one. And this mg, like if you were trying to find the force of gravity on the person, which is this, if we're using g as 9.8, or if we're trying to prove that 9.8, then that's the acceleration of the person as a result of this force. So this mass here would be the mass of the person, which we've called m1. So those two will cancel out. So we have g, acceleration due to gravity, is going to be equal to big G, this constant, times m2, which we said was the mass of the Earth, times r squared, where r is the radius of the Earth. And those are numbers we can pretty easily Google, right? Radius of the Earth is around 6.38 times 10 to the 6th meters. Mass of the Earth is around 5.97 times 10 to the 24th kilograms. And so if we plug those into the equation and we plug in the 6.67 times 10 to the minus 11 for the constant, we get a value of G equals 9.78 meters per second squared, which is pretty close. And, this is obviously, there's more digits beyond this 6.38 and this 5.97. So if I was more precise with those numbers, I'd probably get closer to, the kind of extended accepted value for G, the acceleration due to gravity, the magnitude of it. And so it's just kind of interesting that this quantity that we just memorize and we use all the time, and maybe haven't thought that much about, it is interesting to kind of prove to ourselves and see that it actually does come from the values associated with the Earth itself. So it's the radius of the Earth and the mass of the Earth. And so if you were doing a problem somewhere else, if you were on Mars, say, or on the moon, which seem to be the two really common ones that you might see in a problem, then you're going to have a different mass, a different radius, and so you'll have a different g, a different acceleration due to gravity. So kind of interesting to see where that number comes from. So at this point, I have a few multiple choice questions to use as sort of a check-in. So again, in the chat, I know there's not a ton of people here, but if you can go ahead and respond with the answers right in there, just typing in A, B, C, or D, that'll be awesome so we can kind of talk our way through these. So this is pretty similar to a multiple choice question that you might see on the AP exam. So this is how this law of universal gravitation is often applied. It's not the only way that it'll be applied, but you'll see it like this a lot. So we have planet A is a distance r away from planet B. So if the planets move so that the distance between them becomes 1/2 r, what happens to the gravitational force between them? So we have our 4 choices. It's doubled or quadrupled, cut in half, or cut in 1/4. So go ahead and see what you think and type in your A, B, C, or D in the chat. And one thing I can do while you're thinking, I'll come back to something that has the equation on it. So if you want to, on a paper and pencil or on Post-it, if you've got one near it, just write down what the equation is if you don't already have it in front of you. I'll give you a minute to do that because you kind of need to be able to see that in order to think about these types of questions. And of course, on the AP exam, this is an equation that you will have on your equation sheet. So you'll be able to see that. Okay, so I'm going to assume if you've wanted to write it down, you've written it down so we can come back to the question. So if r is cut in half, r becomes 1/2 r, what happens to FG? What do we think? Okay, so we can maybe try to reason our way through it a little bit. So if we think about the equation that you hopefully have in front of you in some form, the r, the distance portion, is in the denominator. So if it is getting smaller, if it's in the denominator, that means it is maybe not directly inversely proportional, but it's got an inverse relationship to the force. So if the distance decreases, the force increases. So we can tell right away that it's not going to be C or D because they're getting closer together. The distance is getting smaller. So that's going to increase the gravitational force between them. So it's either doubled or it's quadrupled. And to figure out that, if you look at the equation, the distance factor is not just r, it's r squared, right? It's g m1 m2 over r squared. And so that means if the distance is cut in half, then the force is going to be quadrupled, right? Because it goes as r squared. So if the distance was cut to 1/3, you would end up with 9 times as much force. If the distance was cut to 1/4, then you would have 16 times as much force, and so on and so forth. It's that squared inverse square relationship, and it's often referred to as an inverse square law. And it's a pretty common format as well. You'll see other inverse square laws in physics as you go through as well. Okay, let's look at another one, and hopefully we'll get a little bit more response in the chat. I know it's, it's hard to put yourself out there, but let's look at this one. So we have a rocket takes off from the Earth's surface. As the rocket gets farther and farther away, what is going to happen to its weight? So I didn't put a D on this one because it felt kind of artificial. We've kind of covered all the options with A, B, and C. So does the weight increase? Does it decrease? Or does it stay the same as the rocket takes off from the Earth's surface and gets farther and farther away? So if you think you have an idea of what it is, you can put an A, B, or C in the chat, for whether you think the weight will increase, decrease, or stay the same. So I think there's kind of 2 things to think about with this one. The first thing is what we just saw in the last equation, that relationship between the distance and the force. meaning if you get further away, the force is going to decrease. But then the second important thing to think about here is the weight the same thing as the force? And the answer happens to be yes. So when we say weight, weight is the force of gravity. So weight would be a force measured in newtons like any other force. So the answer to this one should be B. It will decrease. So the force from Earth's gravity on the rocket will get smaller and smaller as the rocket gets further and further away from the Earth. The corresponding question to this one, and a distinction that is kind of important, is same question, same rocket taking off from Earth's surface. As it gets farther and farther away, what is happening to its mass? And we already answered this for weight, so I'll give you a second to see if you want to put in an answer for the mass. Okay, so the answer here is going to be that it stays the same. And so this is getting at the distinction that you've probably talked about in class. If you haven't yet, I'm sure you will. This distinction between mass and weight, where they are not interchangeable. And one thing that seems to confuse this is if you're converting between imperial units and metric units, typically you're going to convert between pounds and kilograms, where pounds is a unit of force and kilograms is a unit of mass. However, if we are on Earth and in Earth's gravitational field, we tend to sort of treat them as if they're interchangeable, but it's really important to understand that they are not. And there's not really a good unit for mass in the imperial system, but in the metric system, we have kilograms are for mass. Weight would be measured in newtons because weight is a force and mass is not. Mass is not a force. It's a scalar quantity that can be defined in various ways, but probably the more common one would be the amount of matter in an object. But you can also think of it, and we'll kind of get to this in actually just a second, you can also think of it as sort of like a measurement of inertia. So if you've learned about inertia, you've learned that the more mass something has, the more inertia it has. But actually, inertia is kind of an observable thing, right? You can see how much something is resisting a change in its motion, and the quantity we tend to put on that, or the quantity we put on that, is mass. So you can think of mass as like the quantity of inertia, and you can also think of it as an amount of matter in an object. So mass is a surprisingly slippery thing for something that's kind of, it seems very simple, kind of like gravity itself, honestly. So let's take a minute to look at that then, the idea of gravitational mass versus inertial mass. So this is another thing that the physics exam kind of likes to ask about. Usually in a multiple choice question, just asking if, giving you some sort of setup and asking if it's determining the gravitational mass versus the inertial mass. It's interesting that they ask about that because as far as the scope of AP Physics 1 goes, they're not really different. It's a distinction that really has to do with the way that it is measured and kind of the way that it's defined. But as far as AP Physics 1 goes, they are going to be the same quantity. So if something, if you measure the mass one way and you find the gravitational mass is 10 kilograms, if you measure the inertial mass of the same object in a different, in a different method, you're going to get 10 kilograms again. It's not going to be any different until you really get into like maybe modern physics or like particle physics. You're not going to see any differences there. And so as far as quantity goes, they're the same number. But they are maybe defined sort of differently, and it's more like the measurement of them is defined differently. Oh, okay, so yeah, sorry. You will get the same value regardless of which one you measure. So let's talk about what it might look like to measure each one. So gravitational mass, if you have something like this, a set of scales, a set of balances, that's usually a pretty good tip-off that you are measuring the gravitational mass. So The gravitational mass is measured, and you could say defined, by balancing the object in a gravitational field. So if you are on Earth, then you are in a gravitational field. So if you have, your unknown mass on one side of the scale and you add known masses to the other side until it comes out balanced, then you have measured the gravitational mass of whatever object you put in the side of the scale. And so it is measured and defined by the effect on that mass of the gravitational field, right? How strongly that gravitational field is pulling on it, that tells you how much mass that it has, basically. The inertial mass is measured in slightly different ways. A pretty common setup is to have the mass on the end of a spring like this, and maybe you would pull it and let it oscillate up and down, and then you would measure most likely the period of those oscillations, and then use that to determine the mass. So inertial mass, you can think about it as its response when you apply a force to it. If you think Newton's second law, F equals ma, if you put a force on this mass, what kind of acceleration do you get? You don't have to measure it directly using F equals ma. You would use a different equation for the mass spring setup that I just described, but you are measuring it while it is in a state of change, right? And you are seeing how much it's resisting that change, really. You're seeing its inertia. And so that would be measuring its inertial mass. So a general rule for these types of questions, a rough general rule, meaning this is usually true, but it's not necessarily true, so you should still read the question carefully. If the mass is at rest while its mass is being measured, then probably you are measuring the gravitational mass. If the mass is in motion while it is being measured, then probably you are measuring the inertial mass. And so if you see one of these questions where it's describing, some setup to measure the mass of an object and asking if this is the gravitational mass versus the inertial mass, one sort of shortcut that will probably work is checking to see whether or not the object is at rest or if it's in motion when the measurement is being made. So that's it as far as material to cover. I do have a few more questions that we can go through, and hopefully response to those. And then after we're done with those, I'm open to, answering other people's questions, or if it turns out that there's not a lot of people there, or there's not, nobody there who wants to ask any questions, then we can kind of call it if we need to. But hopefully we can get through hopefully we can get some interaction going and see if people have some stuff related to gravity that they'd like to talk about. Okay, so first question, we'll see, this is kind of similar to one that the other one that I already asked you, the multiple choice one. Kind of variation on a theme. So let's say we had a planet that has a radius that is exactly 5 times the radius of Earth and a mass that is exactly 25 times the mass of Earth. So we did the calculation, we showed how you would get G, 9.8 meters per second squared, using the law of universal gravitation. And it depended on the mass of the Earth and the radius of the Earth. So now we have this hypothetical planet that has these different multiples of the mass and radius of the Earth. What do we think G would come out to be on that planet? So again, I'll wait a minute or so to see what people put in the chat. Just you can answer A, B, C, or D. Okay, so let me come back to an earlier slide. I should have put the equations in with the questions as well, but if I come back to here, where we ended up with this equation for the acceleration due to gravity, where once we canceled out the mass of the little dude standing there on the surface, we end up with the constant times the mass of the Earth divided by the radius squared. So if I go back to my problem here, we saw that the mass is 25 times. So picture multiplying the numerator by 25. And the radius is 5 times. So we've got the radius in the denominator, but remember it's squared. So if you have 5 squared, then that's also 25. So what you end up with is 25 in the numerator, 25 in the denominator, and they're just going to cancel each other out. And so, get rid of this. The answer turns out to just be G. So the effect of the radius, the change in the radius and the change in the mass just cancel each other out. And so G on that particular planet would also be 9.8 meters per second squared. Okay, so the next one is a fairly simple calculation, and also kind of just making a point about the gravitational force. So what would be the gravitational force between you, if we assume your mass is a fairly average 60 kilograms, and a 70 kilogram person who is sitting 10 meters away from you? So 2 people sitting 10 meters apart, both fairly average weights, 60 masses, I should say, now that I've just made that mistake, 60 kilograms and 70 kilograms. But neither of them, certainly neither of them have a mass that's anywhere near the mass of like a planet. So we said in the very beginning that the gravitational field, unless you have a lot of mass, is very, very small. And the gravitational force between 2 objects, unless they have a lot of mass, is very, very small, which is good because otherwise, you know, you'd be attracting things that have mass all the time. It would be chaos with things just flying around all over the place. But we can actually go through and use the equation and just kind of see how small is very, very small. So if we plug in the numbers to our law of universal gravitation, we have the constant 6.67 times 10 to the minus 11th. We have the 2 masses, 60 kilograms, 70 kilograms, and we have the distance between them squared, so 10 squared. When we multiply all that out, we get 2.8 times 10 to the minus 9 newtons. So we have, what, like almost 3 billionths of a newton. And if you've done some previous force problems, you might get a sense of how much a newton is. The thing that I've always pictured, and probably having to do with the Isaac Newton story, if you pick up an apple, the weight of like an apple in your hand is probably on the order of a newton. So picture 3 billionths of the weight of an apple. So yeah, super tiny. And these numbers come out super tiny unless the mass is really big, because this constant G is such a small number, 6.67 times 10 to the minus 11. So that's a very, very tiny number. And so because of that, we end up with very, very tiny forces unless we have masses on the orders of planets or moons or, even man-made satellites, maybe if they're super, super massive. But something really, really big. It has to be really, really big to have a noticeable gravitational force. Other inverse square laws that you'll see later, you'll see. So for example, when you learn about the electric field and the electric force between objects, you'll have an equation that looks really, really similar to that one. But the constant will be something very, very different. And as a result, those forces will behave quite differently from what we see with the gravitational force. But it's interesting to see that they have the same structure like that. Okay, so that's a quick calculation. The last one we can look at, and so this is actually from the 2018 exam. And I had to look pretty hard to find something that is within the scope of this particular stream, this particular topic, in a free response question. So this is actually just one tiny little part of a free response question. I forget how many sections this one had, but this is just part A, that has to do strictly with the gravitational force and not something else on top of it that we haven't talked about on these streams and you might not have seen in your classes yet. So we have the spacecraft of mass m in a clockwise circular orbit of radius r around the Earth, and we're given the mass of the Earth is me. And so in the figure below, you are just making a free body diagram. So you are drawing and labeling the forces, not the components of the forces, that act on the spacecraft. And each force must be represented by a distinct arrow starting on and pointing away from the spacecraft. So in the stream tomorrow, Peter Apps will talk a lot more about free body diagrams, but that language that you see in that question is pretty standard for drawing a free body diagram. It'll say, draw and label the forces, not components. So you are not breaking these forces down into, their horizontal and vertical components or anything like that. You are showing which way the force itself actually goes. And you are drawing them as arrows that start on the object that is experiencing the force and going away from it in the direction that the force is acting. And so in this case, the spacecraft is out in space, obviously. And so it's not encountering any air resistance. There is nothing else touching it. And it is just in a clockwise circular orbit. We're not given any information about whether it's under thrust or anything like that. So there's not really a way to consider that. So really the only force that you could put in this diagram is the gravitational force acting on the spacecraft from the Earth. And it is going to look like that. It is going to be a single arrow directed directly from the spacecraft towards the center of mass of the Earth, and you would just label it FG. In this case, if this was something that was on the Earth, if you had like the typical, block on a ramp or something like that, or something on a pulley, or any of the kind of situations you see come up all the time in these questions, and the ones that you'll probably talk about tomorrow with Peter Apps, if you come back for that stream, you might go ahead and label that as mg. Any guesses why you would not do that here with this spacecraft? So that g, that lowercase g, 9.8 meters per second squared, that's for an object that is on the Earth or close to the surface of the Earth. This is actually an appreciable distance away from the surface of the Earth. It says the figure's not drawn to scale, but it's, maybe some multiple of Earth's radii away from the Earth. So this is not going to have an acceleration of negative 9.8 meters per second squared. This is going to have some other acceleration due to gravity. It is still experiencing an acceleration due to gravity, but it's not 9.8 if you are that far away from the Earth. So you would not want to label that force mg, even though it's a gravitational force, or can sort of think of it as a weight. You would label it fg, and you would analyze it using the universal law of gravitation that we covered in this stream.